Okay, well, it is 10:05, so let us get started. Okay. All right, so welcome everyone to Yui's MS Thesis Defense. He has been working at the intersection of geometry and deep learning for visual odometry. And so just a quick word, in the past 1.5 years that I've known Yui, he has been an extremely sincere and talented student who has brought a lot of insights into the problem. And he has an IROS submission based on this work and other work which is ongoing. And so let's hear it from Yui.
Thank you, Mohan. Thank you all for coming. Coming to my thesis defense, I'd like to first introduce my my committee members: Mohan Chandraker, Professor Nikolay Atanasov as co-chair, Professor Hao Su, and Professor Nuno Vasconcelos. And this work is presented under Visual Community Center in CSC and ECE department in UC San Diego. So I'm going to talk about the work about an analysis of geometry and deep learning based methods for visual odometry. We know visual odometry is a way we can have the localization using images. And first, I'll talk about some idea of visual odometry and the basic pipeline for visual odometry and SLAM, and introduce some related work. And then I will talk about our work about deep key point based camera pose estimation. This work is submitted to IROS 2020, and I introduce more details about that. And then I'll have some analysis on deep learning based visual odometry, especially on various data sets, then summarize the work. So here's the introduction. Let's first think about why visual odometry. Visual odometry is we can get the localization from images. In autonomous driving like Waymo and Tesla, we use the cameras to observe the world and localize the car so that we can drive safely. In virtual reality like HoloLens and Oculus, we have embedded cameras so that we can observe the environment and track the movement of the user to project the animation correctly. In augmented reality like Magic Leap, we also want to observe where the ground plane is in order to put the animation on top of that. So the problem formulation is that, let's assume we have a camera on the robot, and when the robot moves around, they can observe a bunch of images, and we want to know where the robot is and what the road looks like. So here's an example. If we want the robot to drive to Price Center, it can collect a set of images along the trip. And from these images, we want to get the result, just like the Google Map shows the position of the human being. Oh, it's not coming up. Okay, yes. Just like Google Map shows the position of the human for every single image. Okay, so we can estimate the movement from image A to image B. And this movement, denoted as camera pose, can be represented in 6 degrees of freedom. For the change of position, one to another in 3-dimensional world, so it's 3 degrees of freedom. And we're also interested about the orientation, like the camera is looking up or looking down. So it's another 3 degrees of freedom. And we can represent this camera pose in the matrix form. This matrix T, which is a 4x4 matrix, including the rotation, 3x3 matrix, and translation, 3D vector. Now we know we want to estimate the camera pose as a matrix T. How do we estimate it? Let me briefly introduce the camera projection model. Let's assume we have 3D points in the world, and we can use the transformation matrix to project the point to a camera coordinate system. And this 3D point can be further projected onto the 2D image, P here. So this can be represented as this equation from the 3D point transformed to the camera coordinate system and projected by the camera matrix, camera parameters K to a 2D point. So if we have 2D point, 3D point, and the camera parameters available, we can solve for the transformation matrix. That is why the correspondences are important. We're going to see followed. And we can estimate the relative camera pose from one image to another under a camera coordinate system, or the absolute pose of one image under the world coordinate system, just like the position on a map. Once we get the camera pose for every single image, we can plot out the trajectory, just like the red curve here. And with the ground truth trajectory, we can estimate absolute pose arrow and relative pose arrow. So you may wonder, why do we need to use cameras? We have GPS, IMUs available. Can we use that to get the localization? Yeah, somehow yes. But for GPS, they are inaccurate. The arrow is up to meters. And in indoors, we don't have much GPS available. And it has low throughput. Like in a self-driving car system, we need real-time estimation. For IMU, if we use cheap IMUs, they are inaccurate and will suffer from this drifting problem. First, expensive IMUs, they are accurate, but not easily available. For cameras instead, they are actually everywhere. And we can observe many things from an image, just like human eyes. So we now know visual odometry is important, and we can use images to know the localization of an agent. We then jump into a pipeline of visual odometry and SLAM to see how we really estimate the camera pose. Here's the overview on visual odometry. Let's just take an example of two views. We want to estimate the relative pose from image 1 to image 2. We can follow this pipeline from detection, description, and matching to get the correspondences between two images, and then use the correspondences to do estimation to get the camera pose. For the detection step, we want to find the key points. The key points should be distinctive points so that they can be observed repetitively on different images. Once we have the sparse key points, we want to find the correspondences from matching. So we need to describe each single key point using a descriptor. Let's say this point is on the roof, so it should be matched here. And this point is on a car. This point is on the floor. Once we have this descriptor for every single point, we can find the matching and 2D correspondences. For each correspondence, it's actually a 3D point, the same 3D point projected on the two images, so that we can use this relation to solve for a camera pose. And from the correspondences, we can solve for fundamental matrix, essential matrix, and further decomposed into translation and rotation. That is the final output, which is great. But in many cases, we have outliers in the correspondence set. Can you see where the outliers are? Yeah, so somehow there it is a roof, but wrongly projected, matched with a road here, and also another pair of outlier. So we usually use RAMSEC to filter out the outliers and only use the inliers, denoted as green lines, to solve for a camera pose T. That is the basic pipeline for visual odometry. We then take a look at the SLAM pipeline. We use an example of ORB SLAM. SLAM is similar to visual odometry, but we care both of tracking and mapping. We can also use 2D correspondences to find the relative camera pose. And when the 3D points are available and find the 3D 2D correspondences, we can solve for absolute camera pose. But how do we get these 3D points? These 3D points are, you can imagine they are points in the map. So in the mapping step, let's assume we have the 2D correspondences here and the relative camera pose from frame K-1 to frame K. We can do triangulation to lift the 2D points to 3D and further add into the map. We can see the demo here. These points are observed in 2D, but further lifted and triangulated and add into the global map, as shown in some black dots here. So we now know how to have 3D points. And there's another trick to use keyframes. We know when we're taking videos, many frames are highly overlapped with others. These frames are redundant when doing tracking or mapping. So in the ORB SLAM system, we only add 3D points when a keyframe is selected. By analyzing deep into ORB SLAM, we identify several key factors that make this pipeline successful. These are 3 of them, including outlier rejection. During the post-estimation step, we use ransack to filter out the outliers. And it is a keyframe-based system so that we can make the estimation more efficient. And we also do an optimization called bundle adjustment. The idea is that originally we used 2 views to find the relative pose and then triangulate the points into the global map. When there's an error in the relative pose, there will be an error in the 3D points, and the error will accumulate and make the prediction off. But we want to use multiple frames and the constraint on multiple views to correct the prediction. What are the constraints we have? We know a same set of 3D points can be observed by different views. Like these 3D points are observed by the 2 views, and these 3D points are observed by the other 3 views. So we can have these 2D, 3D correspondences, and also have the camera poses available. Using the 3D points and poses, we can do bundle adjustment to correct these estimations. And with the integration of keyframe system, we can make this optimization efficient. And these key successful factors will affect our exploration on the following work. So visual odometry pipeline has been developed over a decade, but there are also still many interesting works being developed. Let's take a look at these works. So for geometry-based or visual odometry, we have ORB SLAM using feature extractor to find sparse correspondences and do the post-estimation. For LSD SLAM, on the other hand, they do not have sparse correspondences. They use the image pixels to do direct optimization. So it is called direct method. For semi-direct visual odometry, they combine the idea of sparse correspondences and direct optimization. And for direct sparse odometry, they use sparse method, but direct optimization and achieve really good result. For learning-based feature extraction and matching method, we know if we want to do feature extraction, we can use SIFT or ORB feature extractor. And there are several deep learning-based methods. LIFT is the first one proposed in 2016. They mimic the pipeline of SIFT feature extractor, but can be optimized end-to-end. For SuperPoint, they use self-supervision to train an encoder-decoder network for detector and descriptor. For LFNet, they try to achieve better subpixel accuracy. And for self-supervised 3D key point, it is similar to SuperPoint, but has more integration of the 3D geometry. And we also see many works about learning-based visual odometry and camera pose estimation. For example, CN SLAM is an early work used the prediction from the network to correct the scale drift for a SLAM system. And postnet, the pipeline is trained using the whole sequence, and then given an image, we can get the camera pose of the image. And deep VO, given the sequence of images, we use recurrent neural network to solve for camera poses. For deep VO, they use unsupervised learning to train the network. For SFN learner, they first propose using two modules. One is depthnet, the other is postnet to get the depth and post prediction. And from these predictions, we can warp one image to the other and enforce the photo consistency loss. For GeoNet, it is similar to SFN learner, but has an additional branch to estimate to predict the optical flow and have the supervision with another branch. For DeepF and Good Correspondences paper, they look into the problem of noisy correspondences. So given the correspondences, we want to find out we want to give weights for each correspondence. Hopefully give low weights to the outliers so that we can have a more robust estimation. These are the works proposed by recently. And we know this field has been actively explored, and many works, especially deep learning-based method, has been proposed. Let's jump into the next session to talk about our work using deep key point-based method for camera pose estimation. This problem, we have the motivation that camera pose estimation is the key for visual odometry and SLAM system. Traditional method like SIFT as a feature extractor and RANSAC as outlier rejection has been proposed and dominated this field for over a decade. But there are some interests using deep learning-based method because we know a network can learn from data. And there are models proposed to replace SIFT or RANSAC, but they are optimized individually. We know there's benefit if we connect these pipelines into a complete camera pose estimation pipeline and optimized end-to-end. We can probably achieve better performance. So we propose an end-to-end framework from feature extraction, matching to pose estimation. And we propose novel modules, including the soft argmax bridge, to connect the feature extraction and pose estimation and make the gradient able to flow back to the feature extraction so that we can optimize the whole pipeline using a pose objective. It is the final goal of the estimation, and we optimize based on this. And we've done ablation study on Kitty and Apollo-Scape dataset, especially on cross dataset setting.
Can I ask a quick question here?
Yeah, sure.
Is this supervised or unsupervised? I see some ground truth pose, so supervised, right?
Yeah, it's a supervised method. Thank you.
Okay.
Yeah, and I'll introduce more details of the two orange box here. And this pipeline is inspired by ORB-SLAM, where we have a feature extractor and form the sparse correspondences and use an outlier rejection during the pose estimation. We replace the ORB or SIFT feature extractor with the deep network. We use superpoint proposed by Magic Leap. It is an encoder-decoder structure. The encoder is shared, and decoder is for detection and description. This network can be trained using self-supervision, so no ground truth included. And we replace the RANSAC with the work Deep Fundamental Matrix Estimation, DeepF, proposed by Intel Lab. So given correspondences, we want to assign weights for each correspondence. Hopefully, inliers will get high weights and outliers will get low weights so that the estimation will be robust. And here's the overall pipeline. Given a pair of images, we want to estimate the relative pose from one image to another. We first fed in, the images fed into the feature extraction module using an encoder-decoder structure to get the sparse key points and its corresponding descriptors. With two sets of detector key points and descriptors, we can do nearest neighbor matching to find the sparse correspondences. Assume we have n correspondences. We then feed the correspondences into the second module post-estimation. This is the point net-like network where we can predict the weights for each correspondence. With the weights, with the correspondences with weights, we can solve for fundamental matrix using SVD. And it can be computed to essential matrix, then decomposed into rotation and translation. Then we get our final result. There are a few modules proposed. We propose a 2D soft argmax module that works as a bridge of feature extraction and post-estimation and enables the gradient to flow back to the feature extraction module. And the whole pipeline is optimized using the ground truth pose. We first look into the first half of the pipeline. An image is fed into the feature extraction module using convolution neural network and get the detection and description. What will the detection looks like? Will it be a sparse key points? Actually, it's a heat map looks like this. So the heat map gives us an idea or a score of how good each pixel being a good key point. So we can see this area has high score. We can probably have good key point in this area, Should we include all the points with high score into our key point sets? Probably not, because many of these key points are redundant. We only want the most distinguished key points in this area. So we adopt the maximum suppression to get the maximum in this local region. Let's assume we have this U0, V0 of this point has 100 and 150. This is the location of this key point. By doing this, we have some defects. Because we only extract the location, so the location itself is not differentiable. We're not using the heat map itself. And it's in integer level because we compare the pixel values for each single pixel. And we know when we're doing post-estimation, each shift of pixel will affect the estimation. So we hope we can have subpixel accuracy as accurate as possible. How can we solve these two problems, especially the non-differentiable one? We want to optimize the feature extraction module using the gradients from the following pipeline. Can we add some network to predict the residual and the residual itself will be differentiable? We can try that, but in our experiment, it's not working well. So we then think of a way to use the heat map itself. Then we propose a way to get the residual from the heat map. We use the 2D soft argmax module where we crop a small patch around the key point and use the module to get the residual on the point. Then the residual can be get like delta U, delta V for X and Y direction and added up into the original U0, V0 to get a new key point with subpixel accuracy. And this new location becomes differentiable through the soft argmax module. The soft argmax module has similar idea as softmax. We have exponential term here and normalized here, but it is weighted through the offset I for X direction to get the delta U, and J for Y direction within the patch to get the delta V. So this equation makes the delta U, delta V differentiable. And the loss and gradients comes through this delta U, delta V and optimize the feature extraction module. Okay, has the pixel accuracy and differentiable. Here's
Can I ask a
yeah,
related question
sure.
here before we move on to the next part? So I'm curious, is it possible to use the whole heat map directly? Why even look for the maxima? Is it possible to match heat maps across images, and are there drawbacks to that, or having the maxima is more reliable?
Yeah, that's a good question. So if we see this pipeline, what we want is the sparse correspondences. Or if you, as you said, we want to have correspondences, it can be dense. But when the correspondences encodes the location of the key points, which means we can have all the locations from the key points. But the location itself didn't include the prediction from the module, which means there's no gradient, there's no differentiable term in this location. So even if we have dense correspondences, this is also like a location which is not differentiable.
Do you mean that, sorry, do you mean that the key point is always a XY position, and because this position is not differentiable, so we can not directly use the heat map to, like, is that the reason for this?
Yeah, so we have some idea of how good a point as a key point from the heat map. And we do a maximum suppression, which finds the location of the best key point. And by finding the location, we somehow do a domain transform and not using directly the output. Let's say the output of this point could be 0.9, but we only get the location like 100 and 150, which is not the output 0.9 here.
I see.
Any other question?
So one question, is it critical to have subpixel accuracy here, or is it just like, is this just about the differentiability?
Yeah, so we actually verify the idea of how the subpixel will affect the evaluation. And what we did is to use SIFT as feature extractor and kill all the subpixel accuracy, just round it to integer. And the accuracy drops in a substantial level. So we verify that subpixel is important. Okay, so should I move on? Okay, so that's the soft argmax module. And let me further introduce the loss function imposed on the camera poses. Let's look into the second half of the module. Okay, so we have the correspondences with gradients, and we can feed in the correspondences into the pose estimation module, use the point net-like network to estimate the weights. And the weights with correspondences will be will be computed for fundamental metrics using SVD. And from fundamental metrics, we can calculate the essential metrics and decompose into translation and rotation. Where can we put the loss? Can we put loss on the fundamental metrics? Yes, we can do so. It is actually the idea from the deep fundamental metrics paper. Using the ground truth pose, we can generate the correspondences and then calculate the Sampson distance loss on top of fundamental metrics. But fundamental metrics is not the final goal of camera pose. It's not the rotation and translation we want. And a good fundamental metrics can sometimes didn't direct to a good translation and rotation. So we hope to put loss directly on the rotation and translation. That is the geometry-based loss we propose, because pose is the final output, and we need to handle the pose decomposition from essential metrics to translation and rotation. When doing the decomposition, there will be multiple solutions of translation and rotation, and we need to find a suitable solution to put loss on. And also at the same time, it should include the gradients. And the loss function can be written down as here. It is a weighted sum of loss of rotation and loss of translation. For loss of rotation, it is computed as the quaternion vector of the ground truth rotation and minus the quaternion vector of estimated rotation when we put L2 loss here. Quaternion vector is just another way to represent the rotation matrix. And for loss of translation, we use the difference between ground truth translation and estimated translation, and at the same time, L2 loss. Okay, that's the details and the tricks of this pipeline. Let's look into the experiments. These are the baselines we have. We use SIF base method, including SIF plus ransack and SIF plus deepf, and also learning based method using superpoint plus ransack and deepf. And the dataset we use are Kitty dataset and ApolloScape dataset. Both of the datasets are outdoors and captured by cars, but they have different scenes. And let's first look at the qualitative results. Given a pair of images, we want to estimate the relative pose between the two images. And we plotted out the epipolar lines from the fundamental matrix. The epipolar lines are plotted using this epipolar geometry equation here. And ground truth fundamental matrix is plotted into blue and these epipolar lines. And estimated ones are plotted in green. And we can see the intersection of the set of epipolar lines is the vanishing points. And we hope the ground truth and the estimated have the same vanishing points. So the points should overlap with each other. And we also plot out the key points. The key points contribute to the estimation of fundamental matrix. So we can observe how these key points affect the estimation. These are the visualization of the baseline, SIF plus ransack. This is our pipeline using end-to-end training. So we argue that we have more balanced key points that lead to better post-estimation. The vantage points better overlap with the one from ground truth. So here's the one from ransack, from SIF plus ransack. They have few inliers because they use ransack and filter out some outliers and lead to some bad prediction here. And the key points are collapsed into regions here. And we also compare our method with SIF plus deepf. So the estimated epipolar lines and these key points collapse into regions. These points collapse into regions. And for our method, using end-to-end training, we can make the key point better distributed on the scene and leads to more stable estimation. This is our results and the baseline results. Okay, let's look at the demo video. It's a little bit slow. So here's the pipeline and network structure. Okay, let me make it slower. The network structure for feature extractor and post estimation and qualitative results. And we compare our result with baselines on Kitty dataset. We first show the result without end-to-end training. So we compared this pipeline, which is baseline without end-to-end training, with SIF plus ransack and SIF plus DF. This is very So we see the pipeline without end-to-end training, the key points are not well distributed and leads to some post error here. And we show our results after end-to-end training here. Also compare with SIF plus Ransack and SIF plus DPF. We see for SIF plus Ransack, there's a post error here. And for our estimation, we have a balanced set of key points, which leads to the correct estimation. We then try to test on another sequence. And also show that there are collapsed key points on SIF plus Ransack and collapsed key points on SIF plus DPF, which leads to some post error. And for our pipeline, we can have more balanced key points. Here's the KITTI trajectory plotted for sequence 9 and 10. Our pipeline plotted in green is better aligned with the ground truth. And then we test on the cross data set setting. So the model is trained on KITTI, but test on Apollo escape. And this is the model without end-to-end training. And this is after end-to-end training. Okay, so these are the qualitative results. We then take a look at the quantitative results. We can calculate the rotation and translation error, comparing our estimation with the ground truth, and then compare the error with the threshold and calculate the inlier ratio. We hope all the poses are inliers, so 100% is the best. And here's the experiment results on KITTI dataset. The model is trained on KITTI dataset and test on KITTI. And we compare with learning-based baselines using SuperPoint plus Ransack. The prediction is pretty low. And we can, after end-to-end training, we can boost the performance up to 90%. And we also compare with SIF based baselines, like SIF plus Ransack. We argue that our baseline works better than SIF plus Ransack and work comparable with SIF plus DPF. And on a cross dataset setting, we train a model on KITTI and test on unseen dataset Apollo escape. We once again boost the performance for the learning-based baselines. And for SIF-based baselines, the SIF plus Ransack method works the best because there's no overfitting problem. And our pipeline works better than SIF plus DPF. In summary, we propose an end-to-end framework for feature extraction, matching, pose estimation to get the camera pose. This pipeline is connected with a SoftArgMax module to make the gradient available and optimize with the ultimate goal, a geometry-based loss using camera pose. And we performed cross-dataset evaluation to prove that our pipeline can generalize well. One of the limitations of this pipeline is that we're working on the camera pose estimation using only 2 views. Although we can perform on all the consecutive frames and get the whole trajectory, it's worthwhile to explore a complete pipeline on the visual odometry setting using multiple frames. On the next session, we look into an existing deep learning-based visual odometry method and evaluate on various data sets. The motivation is that we see deep learning-based methods somehow outperforms some geometry-based method on kitty dataset, but we hope this method can work well on various environments. So we do the testing. Among all the deep learning-based method, we use a SDFM learner, which is similar to SFM learner. They have depth-net and post-net to get the depth and post prediction. We can then use the prediction to warp the image B to image A and enforce the photo consistency loss. And the difference is that they propose a geometric consistency loss on the depth prediction, so that they can fix the scale drifting problem. And we test on kitty and Apollo and URAC dataset, and for the depth and post prediction. Let's first look at we use the two datasets. URAC dataset is an indoor dataset, and they have only gray images available. Here's the visualization of the depth prediction. Given the input images, we use postnet to predict the depths. It looks reasonable. We have the white area, which is far away from the camera, and the black area close to the camera. And we use the same model trained on kitty dataset and test on URAC dataset. Here's the depth prediction from the input image. It's reasonable that this area is brighter because it's far away, and this area is dark, but they are coarse and tends to be erroneous. And then we test the post prediction by plotting out the trajectory using the same model trained on kitty. We test on kitty dataset, and the ground truth trajectory is plotted in blue, and our estimated one is plotted in orange. And we can see the estimation is pretty much aligned with the ground truth. For the URAC dataset, the ground truth is plotted in dashed lines, and ours is plotted in the colorful line here. We can see the prediction is pretty off, and it tends to predict the translation motion of forward translation. It is an overfitting problem of kitty data because the kitty data set has mostly forward motion, and the rotation here did not discover by the model. We then compare this trajectory with the result from ORB SLAM, and this is the prediction from ORB SLAM on kitty and URAC dataset. Which one do you think worked better? So I think SCFM learner works better on kitty dataset. They adapt pretty well and didn't have much scale drift problem. The ORB SLAM has much scale drift problem here. But for URAC dataset, ORB SLAM predicts pretty well and pretty much aligned with the ground truth. And the problem lies in the domain gap between kitty and Apollo scape dataset, between your kitty and URAC dataset. URAC dataset, they have different scales in indoors and different lighting conditions, and also only gray images available. And there's overfitting problem as we observed before. Can we try to solve these problems? There is some inspiration from ORB SLAM. We know they do optimization using bundle adjustment so that they can enforce the constraint using multiple views to fix the error. We can do similar optimization, but in our case, we don't have 3D, 2D correspondences. So we can instead using the photometric consistency between multiple frames and enforce this optimization. And we can adopt the idea of keyframes. Keyframes are representative and they tend to have large baselines for the 3D geometry. We can use the idea for testing and training. That's a possible future direction. And let's go into the summary. We look into the problem of visual odometry to get the localization from a bunch of images. This is useful for autonomous driving, VR, or AR. We give an overview on visual odometry pipeline and also an analysis for geometry-based system using ORB-SLAM. We identify the key factors, including outlier rejection, keyframe-based system, and optimization. We then propose a pipeline using deep key point-based method for a camera pose estimation. This pipeline includes key feature extraction to correspondences and pose estimation. The whole pipeline is connected with 2D SolveArc Max and optimized using the ultimate goal camera pose. We gave an analysis for existing deep learning-based system using a CFM learner. We identified the limitations and also propose a method to solve it, a potential method in future work. So for our future directions, there are several key factors observed from geometry-based method, which can be integrated into the deep learning-based method in order to have a more robust visual odometry pipeline. For our deep key point-based camera pose estimation, we can further extend it into a visual odometry setting using multiple frames. And we hope to combine the geometry-based and deep learning-based method by leveraging the advantages on the two ends. So in the future, we can have a robust visual odometry pipeline that can work in different environments and enable the various applications. So that's it for the presentation. I'd like to give acknowledgement to my advisors. Thanks to the committee members, Professor Mohan Chandraker, Nikolay Atanasov, Hao Su, and Nuno Vasconcelos. Thank you for your advice during my master program. It's very helpful for my learning and study. And thanks to Professor Mohan Trivedi, I'm working as a TA for his classes. Thanks to Professor Xiaoyi Chen and Dr. Bo-Chen Wu when I was studying in National Taiwan University. Thanks to Wei Chao and Trista during my internship in Inventec. And thanks to Stephanie Matthew in EC department for all the logistics during the master program. I'd like to thanks to my friends and coworkers. Thanks to Ray for working together on this project. It is exciting to have this work. Thanks to Bowen, Jiayuan, Shuang, Ishit for the support in my studies. And thanks to Fred, Joseph, and Vanessa for the support of my life in UCSD. And the acknowledgement for my friends for the trips we had in San Diego. And thanks to my family, my mother, father, and my brother. Thanks for their endless support in my life. Thank you all for joining. Any questions are welcome, and feel free to look into my GitHub repository. There are some codes shared there.
Okay.
Thank you. This was very nice.
Okay.
Thank you.
Okay. All right. If there are any quick questions from the audience, we can take them before moving to the private questions.